Okay. Wow. Good. Okay, let's get started. So today we will talk about heap and how to exploit heap vulnerabilities. So this is totally another beast. Very complicated stuff, um, even compared to ROP and everything we learned before that. We will break this down into smaller parts and divide and conquer each part. Um, and Also the heap implementation, it's constantly changing. Because of that, it's also new vulnerabilities discovered, then new defense proposed to patch that, and sometimes um, new solutions were developed to make it even faster than new security vulnerabilities are discovered there. Which makes this a very dynamic area for hacking. Um, so uh, first, first of all, let's say what is Heap? So I bet at this moment you're already familiar with this memory map of a Linux program. Of course, other systems, they also have a map similar like this. So, so heap is an area, is a pool of memory that is persistent during the program execution. So it's not a stack, right? So stack goes from higher address to lower address. Heap usually goes from lower address to higher address. So stack is for each thread, each function, and it's dynamic. Only when that function is executing, we have a stack for that. But when that function is not executing, that memory is reused for other functions, or no one is used that. So heap, we have memory that is persistent for the program. Programmers can dynamically request those memory regions and also release those memory regions at runtime. So basically, heap is a pool of memory used for dynamic allocations at runtime. So the keyword here is dynamic and runtime. Basically, they mean the same thing. So stack, when you have a local variable, that local variable, the memory address technically is not allocated at runtime, right? So the compiler already allocated that address. The compiler did, after the prologue, the compiler did something like subtract EBP a constant value, right? At runtime, the EBP value will go, ESP, sorry, not EBP, or RSP will go down. And that is to reserve that memory. Even though that instruction is executed at a runtime, that instruction was emitted by the compiler. The compiler already determined that we're going to do that when you execute the program. Then that the location of those local variables, they are just an offset of RBP or EBP, right? However, heap is dynamically allocated. The memories in heap are dynamically allocated, and also they are persistent between functions. So you're probably familiar with several interfaces the heap provides, right? The first one is malloc. The malloc will grab memory on the heap and return the memory address to you. Also, C++ have a keyword new. Also, other languages like Python, they also use a lot of heap. So any significant normal applications, they will use heap actually. Then corresponding to allocation with malloc, we also have free to release memory on a heap. Also, we have a delete keyword in C++. So those functions, malloc and free, they are standard C library interfaces, okay? They are not system calls. A lot of functions we learned so far, like open, close, send file, we talk about the C library function, right? So those functions, they have a corresponding system call. Those functions are basically a wrapper of system calls, but those two functions are not. Okay, they do not directly map to any system call. There is no system call called malloc or free. So you may ask, if we want to get some dynamic memory, why don't we just do memory map, which is a system call, mmap? Actually, we can do that. The problem is, if you want to do a system call, it means you need to go into the kernel. The kernel will do a lot of work, so it's very slow. And what you are doing here may not necessarily need the kernel, right? The second thing is malloc only provide an interface that allocate pages of memories. It cannot allocate 20 bytes, 10 bytes. It doesn't do that. It can only allocate 4 KB, 8 KB, 16 KB at least for you, right? Because of that, we have the idea of dynamic memory allocator, which is a user land program. It's not in the kernel. And this user land allocator program will interact with the kernel, and sometimes do not interact with the kernel that often, actually. So there have been many implementations of dynamic memory allocators. The idea of malloc, free, those interfaces, they were probably proposed in the 70s. So if you Google this, you can find in the 70s, people have been proposing that. And one of the most popular one, the heap management program or dynamic memory allocator, is the Dog-Lee malloc or DL malloc. So it was released to public in the 80s, and Linux picked it up. So Linux was using that for many years. That's why it's get very famous there. So currently, the version of memory allocator we are using on our server is called PT malloc, and it was based on DL malloc, extended for use of multiple threads, and it is still going through a lot of development, a lot of changes. Every version of C library is updated. There's a lot of changes. Google, they also developed their own memory allocator. So all those allocators, they have the same interface. Remember that. The interface is malloc, free, panloc, and also new, delete, those things. The same interface, but the internal implementation is different. Just like all other C libraries, there may be different versions of C library implementations, but they provide the same interface, the functions, open, core, fire, fopen, those things. Also, free BSD, Firefox, Android, they use another JE malloc, which is a totally different design, which we will not cover in this class. Also, there is a professor in UMass Amherst, Emery Berger. He maintains his own allocator, which also has some people use this. Besides those userland, those are userland malloc for applications. The kernel level, we also have their own memory allocators. Kmalloc is Linux kernel memory allocator. So in Linux kernel, when you need a small piece of memory, you want to do a malloc, you don't use malloc, you use kmalloc. Okay, the function's name is kmalloc, because malloc is a userland application. Even, I mean, in the kernel, when you want to print something, you do not do printf, because printf is a C library function. The kernel version of that has a slightly different name. So to separate, we are in the kernel. iOS has their own memory allocator, panloc. Windows has their own version as well. So those interfaces provided by memory allocators are malloc, free, and they are defined in the std leap header file. So malloc is to allocate some bytes of uninitialized storage. If the allocation succeeds, the function will return a pointer to that memory location. Okay. This is very important because later we will see the underlying working of this. You will find something surprising actually. Then free will deallocate the space previously allocated by malloc or calloc, which means this is the developer's job to do this correctly. Malloc something, then free something, okay? If you do not free something, you just malloc, then you have a memory leakage, which means that piece of memory will never be used again. If you malloc once and free twice, there's undefined behavior. If you free something which was not mallocked, you also may trigger some errors, right? And when you hear about errors, that's where attackers can exploit, right? So that's what we are going to exploit. So besides malloc, there is also the calloc interface. The calloc interface takes two arguments, number of items and the size of each. You multiply them together, you get the total size. And the difference between malloc and the calloc is that malloc doesn't set the memory to 0, but a calloc will initialize that memory location to 0. That's it. Okay. I don't know why they have a different prototype here, maybe just to separate them and to make them look different. Also, there is a reloc function to resize the memory block pointed by a pointer that was previously allocated by malloc to change the size. It may be successful, it may not be successful. So those are the basic 4 interfaces, 3 about allocation, 1 about free. Okay. Yes, exactly. It's more complicated under the hood there, but that's basically the idea. That's one of the ideas. Yeah, the memory reuse. Yeah. Yeah.
So for the reloc, when you change the size, say it could fail, what kind of cases can the function fail?
For example, let's say we have a memory chunk like 20 bytes, and before that, after that, we already have other memory chunks. Now we're requesting at the same place, we're asking 50 bytes. Well, it's basically cannot do that. One way to do that is to move this part. Maybe the current implementation is not going to move this part, so it will fail. It will give you another memory place. Yeah.
Then fail or it gives us another memory.
Yes. Yeah.
Fail or it gives you another memory.
Fail means it will not be able to give you the where you are asking for.
But it will give you.
Yes, it will give you. Well, it can still fail, means totally fail, like you cannot find a memory for you. That happens too. Yeah. That also happens for some other memory allocation interfaces. I think like mmap, you ask kernel for a memory, several pages, something like that, memory map. So in memory map, there is a parameter that you can suggest to the kernel, this is a memory I want, but the kernel doesn't guarantee it will give that memory to you. Yeah, I think memory. Yeah, we can check that. We can go to any of those. Now we just do mmap. See, mmap has an address. Okay, so you can ask for that, but the kernel doesn't guarantee it can do that for you. A very simple example how to use malloc. You just use malloc with a number to request memory. Then you just free it. That's it. Okay. This looks very simple. You have a malloc, you have a free. However, if you are developing a multi-thread program, and they may use the same malloc memory, and there is risk conditions. The thread may run, one thread will run first, another thread may run later. Things get very complicated, concurrency problems. Then you may free something before it is mallocked. You may free something twice, right? Those errors can happen. So if we compare heap with stack, then we can say the stack memory, they are fixed memory allocation, lower at the compiler time. The compiler already emit those subtract RSP number instructions there. So stack is used to store local variables, return addresses, function arguments. This is very fast. How fast it is? It's just one instruction, subtract RSP number. Every time you want to refer to an address, it will just be RSP plus something, RBP minus something, right? Or EBP minus something. That's very fast. And it abstracts away the concept of allocation and also release here. Heap is dynamic memory allocation at runtime. Usually we use it to allocate persistent objects, persistent buffers, sometimes also bigger objects that usually stack is not easy to handle. Compared to stack, it's slower, but it doesn't necessarily go to the kernel. It's not that slow. It's slower because you are calling the function malloc to get the memory, right? So here stack, you're getting 10 bytes, just one subtract, then refer to that address as RBP minus 10, 20, whatever, that's it. Here, you need to call into a function, and that function could be very complicated. There's a big library behind those functions. So it's much, much slower, many, many more instructions. So one malloc may be thousands of instructions, more than 10,000, 20,000 of instructions. Here we're talking about one instruction. Even here, so this is much slower, but not necessarily need to go to the kernel. So on our server, the version of memory allocator we are using is PT malloc 2, and you can find the source code at those places. Okay. If you want to check the version, you can just do a LDD version, and it tells you that this is the C library we're using. Of course, this is a default one. Whenever you run any program, you can use the Linux trick LD preload to use other libraries. But here we're using the default one. Okay. So the version we're using is 2.31. Okay. This is very complex stuff, and its implementation is constantly changing. So I'm trying my best to approximate to this version of PT malloc. Yeah.
Every time it doesn't need to go to the kernel.
Yeah.
I would assume that whenever you have to access and
so what kind of resources you're talking about? Yes, here we're talking about memory resources, right?
every time it doesn't.
No. So all the applications you saw, right? Like the stack. When you access a stack variable, local variable, did you go to the kernel? You didn't. You go to the kernel only when you make the system calls. Right? So here the same thing. Yes, but you can request a huge chunk of memory first. Then the usernet library, the libc, the memory allocator will decide how do I slice them into smaller pieces and give to the application? That's why you need to go to the kernel. Of course, at the beginning, you need to go to the kernel. When you do not have enough memory, you go to the kernel, but not every malloc, you need to go to the kernel. Yeah. Make sense? So this slide actually answers your question. So when do we need to go to the kernel, right? So how did ptmalloc get a memory in the first place, right? Then there are several ways to do that. You can use mmap. So ptmalloc use mmap when you request for huge memories, like several megabytes or even bigger. They can use memory map. Or when they do not have enough memory, just use two system calls, the break system call and what is S break again? I don't remember what S stands for. Does anyone remember? Okay. Okay, anyway, break and S break. So the S break system call, if you give a parameter 0, it will return the current program break. Okay, that's a concept, program break. But this is a concept we have saw at the very beginning of the class. Okay, so this phrase is called the program break. Okay, so basically, this is talking about the end of the data segments of the program. Okay, the end of the data segments. The data segments include the heap, include uninitialized global variables, and also initialized global variables, and many other things as well. But this is the end. Okay, so the program, when you make a system call sbreak with the parameter 0, the kernel will tell the program your current break is here. If the program wants more memory for the heap, it will also call the sbreak. It can call either sbreak or break system call to do that. If we call the sbreak system call, it can move the program break up. Okay, so under the hood, the kernel will actually allocating memory for you for those places. Also, you can do break. So sbreak, you give a number, then the kernel will increment that many bytes for you. Or break, you give an address, then the kernel will make sure below that address, the whole memory region will be usable for you as a heap. So those are two different system calls. What? Yes, if you do not have enough memory, the kernel cannot do that, the kernel will tell you. Yeah. Okay. So the concept here is the program break. So if you just do man, sbreak, or break, you can get this description, program break. Yeah.
Put that break over there, right? So like, does it preempt? Okay, like by so now I need to probably allocate this much amount of space like this to a heap dynamically allocate. So does it preempt?
Yes.
Amount of
there is another system called is memory map, right? No, memory map, we use memory map to load libraries usually. Yes, so those are mainly for the data segments. So we can do this. We actually did this before. Let's see. So now we have a program here, right? Oh, what's going on? Let's just do a strace. So random program we have here. So here we have a break. Okay. So this break and S break probably the same. It will return where is our program break. Here's the program. This is where's my program break. But you didn't code this part. This is still the libc start main, whatever, code is this part. Now after that, here we are trying to get some memory to load the libraries. See, we're using mmap2. It's another variant of mmap. Here another mmap2. After we load those files, we actually close them. Yeah, here's another. This one is not the library anymore. This one is the actual program, I think. Looks like. Oh, this one is still a library. This is this library. So this is the libc library. Yeah. Then we have mmap2, and you can see here we do not have. We do not have S break, but we do have two break here to change our program break here. Okay, and this is not done by. Oh, this actually may be done by us because we have a malloc there. Yeah, because we have a malloc there, then there was no heap at the beginning. The memory allocator finds there's a malloc, then it makes this system call to get some memory.
Break none for the finger and then the address that means it's the malloc is that's where malloc is happening.
Yes, so somewhere here we are making the first malloc.
What I basically return the location of the.
No, only if you give this one, right? This one returns the higher address of the heap, the setting of the heap, not the address of the heap. So here you can say, it first asks where is the setting of the heap. Then we are requesting one more page here actually. Yeah, from A to B.
It's not changing, it is requesting one more.
What do you mean by changing?
You have to give the top point for it, right?
Yeah.
But if I pass that address, it will break it. Going to change it.
It will change, yeah. It will change the program break to a higher address. Under the hood, the kernel will actually allocate the memory for this part. Yes. So allocating memory is more than just changing this global variable, obviously. I mean, kernel global variable. Yeah.
Can you only extend the program break?
You can make it smaller. Yeah.
For the stack, you need another map.
For stack?
The first map should be for library and then our own text and data.
No, stack is determined by the value of ESP or RSP. You at the very beginning, you need to allocate some memory, then you set the RSP, ESP to the top, then you just keep going down until it reaches end. Then we could be a segmentation fault or whatever. Yep.
So if I am adding some space onto the heap using break, will the information that I enter grow up in this space that I reserve? Like if I have space 100 and I've added another 100 spaces, so I have 100 to 200 as new area that I've allocated. If I enter in something that takes 96, will that go from 100 to 196?
So here we're talking about two different things.
Yeah.
So when you use the word allocation, it maybe means the allocation at the user land level. It also means the allocation at the kernel level, right? The kernel level is a real thing, right? So the kernel level, the interface is very coarse-grained. It's not fine-grained like I can ask for 200 bytes, 100 bytes, right? Usually if you use mmap, it will be 4 KB at least. And even if you do not use mmap, you use break, it probably will also like 4 KB. That's why you say the example there, we're jumping from A to B, right? So you cannot do a very small one.
Gotcha.
Then, after the kernel return a big chunk of memory to you, let's say 4 KB, then at the user land, the memory allocator will manage that 4 KB. And from there, the interface will be malloc and free. And malloc or free, you can do very fine-grained memory management. You can do 4 bytes, 5 bytes, 10 bytes. You can do that. Yeah.
So is that using the big endian versus little endian?
What does that matter? What do you mean by?
I'm trying to figure out what direction the data is
Oh,
growing inside the heap.
the data goes from low address to high address. Yeah, so that's different from stack.
Yes.
So heap goes this way, stack goes that way. There are some historical reasons for this. For older machines, they have both stack and heap, and what is the best way to utilize most of the memory is to set both of them to going towards each other,
yeah.
Right? Instead of a predefined, oh, heap will be this size, stack will be that size. So that's a historical reason, yeah. But now we also have mapped memory. Everything's complicated. Okay. Now we are going into the very complicated stuff. Okay. The first concept or data structure we will learn is this malloc chunk data structure. So this is a data structure to store the data and also to represent the memory chunk to store your data, okay? And there are many different versions of this. If you go to the source code, it can be quite confusing because if you go to this version of source code, 2.31, this is what you are going to find, okay? But this part is also confusing because for most cases, we're not using this part, okay? I will show you later. So this version, I call it the no Tcache version. So later we will explain what is Tcache and how the Tcache version will be different. So this structure, malloc chunk, has 2 different states. In 2 different states, they have different internal members. One state is this memory chunk, the malloc chunk, is in use. It is currently being used. It just been mallocked. It has not been freed. That means it's being used, in use. Another state is it was mallocked before, however, it was freed, which means you can malloc it again, reuse this piece, okay? And that is called freed state. So the first 2 members of this structure is, the first one is called previous size. It's you allocate many malloc chunks in the memory one by one, and they have different size, okay? One could be 20 bytes, the second one could be 2000 bytes. And this field records the previous chunk's size, okay? That's the original design. Okay. Then the second field records the current chunk's size, okay? And those 2 variables, their own size is size t, which means 32-bit machine, both of them. This one is 4 bytes, the second one is also 4 bytes. For 64-bit machine, this one is 8 bytes, and this is also 8 bytes. Okay. Then after that, this is where things are tricky. If this chunk is in use, someone mallocked it, you don't have those structures. You don't have this part, okay? What you have here is your data. This is a buffer. So when you do malloc, this is the address malloc returns to you, okay? Not this address. So you do malloc, you copy data there, it's copying to here. Yeah. So you didn't know that before that there are 16 bytes in your 64-bit machine, 16 bytes of metadata, or 8 bytes of metadata in a 32-bit machine. Okay. Your data goes here. So what if this is a freed memory chunk? So this is not being used. So then you don't have data here. So when there is no data, we have several pointers to form singly linked or doubly linked links to maintain a free chunk links. We have many of those, and those are those fields. There is a forward field, there is a backward field, there's another for large ones, there's the next size and forward exercise, backward exercise. So if you go to the source code, this is what you get. Yeah, okay. But this is I have more examples for this. Okay. Let's say here, this is directly taken from the source code. The source code has this explanation. How many chunks we have here? We actually have 2 consecutive chunks here. First one is called the chunk. The second one is called the next chunk. Okay. So each malloc chunk has the same format. It has the metadata, then it has the user data, right? So in this case, we have the first chunk has the size of previous chunk size. The previous chunk, we're not seeing it here. Then the size of the current chunk. And this size is the total size of the chunk, not just the memory you request. You request malloc 4. And the chunk size will be much bigger than 4. At least there will be those metadata, and also there will be alignment. Okay, so the alignment in this case, I think for 32 in 64-bit machine, alignment will be 16 bytes, no matter it's 32 or 64-bit program, it will be 16 bytes of alignment, which means the chunk can only be 32 bytes, 16 bytes. It cannot be 16 bytes. If you have if you are 64-bit program, you cannot be 16 because the metadata takes 16 bytes already. It can be 32 bytes, 48 bytes, 64 bytes. It cannot be 62 bytes, something like that. Then, because of that, because of the alignment, then we do not really, in the size field, we do not really need all the bits, right? Because we always align, in this case 4, we actually say 4 bits. But right now we're using the last 3 bits for different things. The last bit, the P bit tells whether the previous chunk is in use or it's freed. Let's say we have 2 chunks here. For the first chunk, we cannot see the previous chunk, so we ignore its bits. For the second chunk, we know the previous chunk is in use, so the P bit should be 1, indicating the previous chunk is in use. Then the second bit shows whether this chunk was obtained through memory map system call. Okay, so in most cases it's not. In this case, it's 0. The third bit, we're not going to use it very often in this class, talks about whether this chunk belongs to a thread arena. That's another concept we will not talk about today. Next week, we'll talk about that. So this is the no Tcache version. So when you do malloc, and this is what malloc returns to you. Okay. So when you have also the no Tcache version, if this chunk is freed, then after that metadata, we don't have user data, right? We have more metadata. We have the forward pointer to the next chunk in list and a backward pointer to a previous chunk in the list. Okay. But that is only the no Tcache version. Unfortunately, what we are using on our server and your current laptops is more complicated than that. We're using something called the T-cache design. Okay. It's on top of the ptmalloc design we just saw. That's why the ptmalloc, the code, you go to check the code, it's still there. It used something called the thread local caching. The purpose of this design is to speed up repeated and small allocations in a single thread. Okay. So imagine you are develop a web server. The web server will request a lot of small memories, several hundred bytes, or even 200 bytes to pass the web request. And after you pass that, you release that, you repeatedly doing that. And this is an optimization for those. So in this T-cache design, we do not have the previous. We do not have those parts anymore. Okay. It's actually very complicated. For small memory pieces, we don't have those parts anymore. That's why it's so complicated. For small pieces, we don't have those. Okay, we don't use those anymore. We use another design. Okay. Let's go back here. Okay. So in this T-cache design, this is a multi-thread scenario. Then each thread for those small memory allocations, they will maintain many singly linked lists. Okay. It's a single list, means one item will point to another item, and this item doesn't point back. Okay. If it point back, it's a double linked. So here is singly linked. Okay. Then this is like a global variable for each thread. Each thread has many bins for different size of memories, like 16 bytes, 32 bytes, 60 bytes, small memories. We're not talking about like a 4K. We're talking about like up to 1,000, something like that. Then each of them, we group them together. For 32-bit, 32 byte of memory chunks, we have so many chunks, okay? We link them together. For 500 bytes of chunks, we link them together. They are free, we link them together, right? And this is a global variable. This is a type of that global variable to define that. So defines how many bins there are there. Usually, I think the current implementation has like 64 or 63 bins. The size from 16 bytes to 512 or 1024 bytes. Then it has the pointers to that. So this is the global. This is a global variable for each thread. Then for the bins, basically a bin is a list of free chunks, not non-allocated chunks. We put them in bins, okay? And bins are differentiated based on the size of chunks they contain. And they have many concepts: fast bins, small bins, large bins, unsorted bins. We're not going to talk about the details today, but eventually we'll talk about. Today, we mainly focus on fast bins, small bins. Okay. This part, I guess we can skip for now. Let's go to the metadata part. So this is still the malloc chunk. So when this one is in use, this is our data part, right? When this one is not in use, this is a freed one. For freed one, we have different metadata for this part. And the metadata we use here looks like this. For fast bins, small bins, this is the metadata we use. Previously, we have 4 pointers: forward, backward, forward next, backward next. Now we only have 2 pointers. Okay. So previously, it was doubly linked because you have forward and backward, right? Now, this is the T-cache entry, and the first T-cache entry member is a T-cache entry pointer to the next one. Okay, so this is a singularly linked data structure. Then after that, we have a key. It points to the global variable, and this field can be used to detect a double freeze, but it can detect some special cases. Anyway, the key here is now we have two pointers. One is for the singly linked list. Another one points, everyone points to the same thing. Okay. So those are for small memory chunks. They are in the fast bin or small bins. Now we have the key actually points to the T-cache thread structure, which is a global structure we showed before. Yeah. Okay, so let's say this is one example. I stole this from my friend Yang at Arizona State. Okay, anyway, so let's say we'll have one thread here, only one thread, and that one thread has that T-cache per thread structure. We call it bun, and that's the structure we just saw. It has many bins, right? We have different bins. Each of them is like a bin here. Okay? Actually, the list is like a bin. Okay? So this is like the header, the head of the bin. Right? So first, the first member there is counts the number of members in this list. Obviously, that field is not necessary because as long as you have the list, you can traverse to get how many are there. So that's just for performance. And that is actually written in the document. Let's say, I think the document explains that somewhere. Yes. So in the source code, the C library source code, if you read the comments here, it says that counts are actually redundant. We don't really need this one, okay? Because if this is a list, you traverse the list, you get the number. This is just for performance. So first of all, let me ask you, what are those? What's the name for those? Yes, malloc chunks. Yeah. So each of those is a malloc chunk data structure. And what does that data structure look like? So at the beginning, there is previous size, current size, then it has next and key, right? So here we're pointing to the middle of that data structure actually, because we're pointing to the T-cache entry instead of pointing to the beginning of the chunk, right? The next question is, are they in use or are they freed? Yes, they are freed. Only when they are freed, they are in the list. When they are in use, they are not in the list. Okay. So in this case, we have many bins. Let's say there is a bin for the size of 16, bin for the size of 22, bin for the size of 48, which means this chunk, the size of it will be 16, or obviously this can be only be a 32-bit machine in this case. So I think we should update that number. A little bit confusing. Then in this list, we have two chunks. The header points to chunk A, and chunk A's next field points to chunk B. And chunk B is end. That's why the next field is not there. And they have the same key here, points to this data structure. Okay. Then for the bin for the size of 48, we also have one chunk, because there's only one chunk, means only right at this moment, only one free memory chunk for this size is available. Okay. It doesn't mean if we're requesting 48 bytes, And let's say for this one, 64. If we're requesting one, we are requesting a memory for 64 bits or 50 bits, whatever, bytes, whatever. There is no available ones. Does that mean we cannot get a memory chunk for that? Not really, okay. Because this one, those bins only store the free ones, or freed ones, not free ones, freed ones, which means previously mallocked, then it was freed, we save it there. If we want to get new memory, we just get new memory. We don't have to use previously freed ones. Make sense? Yeah. So how do we get here? Let's see. So, yeah, go ahead.
You said the key headed to the with
The the global, the per thread structure.
Oh,
yes.
If you have multiple threads, it will have different keys.
Yes, yes. That's the current design. This is changing every day. Yeah. This is our source code here. We have A, B, C, D, E, F. We malloc 16, 16, 32, 84, 48, 32, 32. Then we malloc again. 64, 64, 64, and XYZ. And we free B, A, F, B, C, D. After we run all of those statements, this is the end result. This is what it looks like. Okay. So first of all, A, B, C, D, E, F, we mallocked them, then we freed them, right? Because we freed them, now they are managed by this structure because they have been freed. Okay. X, Y, Z, we never freed them, so they will not be in any of those lists. Okay. Okay. At the very beginning, this structure for freed memory chunks doesn't have anything. We don't have freed yet. We have been mallocing a lot, but nothing has been freed. So no one is really linked to there, okay? Now we're going to free B. We're going to free B, and B is going to the bin for 16 bytes of memory chunks, right? Which means this head will point to this B's memory chunk, and B's next one will not point to anywhere, this last one. Now we're going to free A again, okay? A and B had the same size. So what we will do is the memory allocator will insert A back to the head of this list, not the tail of the list. That's just how it is designed right now, which means this pointer will point to A, the A will point to B. Okay. So after we free A, we will have something like this. Okay. So now we're going to free F. F has 32 bytes, so it doesn't belong to the bin for A and B. If you go to another bin, then it will go to the 32 bin where it points to F. And we'll go to E, which is also 32 bytes in this case, then E will be inserted into the head. So this head will point to E, then E will point to F, right? Then we free C. So C, the head will point to C, C points to E, E point to F, right? So why we are doing this? Why are we inserting into the head instead of the tail? Exactly, right? This is what you learn from, yeah, this is what you learn from your data structure course. If you want to insert to the end of the list, you have to traverse from here, right? If you want to insert to the head, then you just get this pointer, which is constant time, right? That's why we're doing this. Yeah. It's faster. then we have D here, then D will also be free. Now X, Y, Z, they're not freed, so they don't have next, and they are not managed by their key doesn't matter either. In this case, their key doesn't matter because they are in use, right? So those have user data. Yeah. Okay, so we can summarize this way. So in Tcache, for those small, yeah.
Say the malloc from the buffer.
Yes.
Finally, what is going to be start here, and then you have what would have been the next pointer and the key pointer, and then you overwrite them. Like, is the data overwritten down, or is it?
They overlap. They are the same address. But
obviously the two entries are just 4 bytes. For
yes. Yeah.
Which is like 64 bytes. So the rest of the whatever.
Doesn't matter. They will stay there.
Oh.
We'll be above. It's a higher address. For each data structure, obviously, the first member is at lower address. Later members are at a higher address. Yeah.
Continue after.
Yes.
And the
Yes.
size parameter, because of the size, we know how long.
Yes. We know how big it is. Yeah. So actually, I think this part we can skip, then we can revisit this next week. Okay. So after what happened just now, we already freed A, B, C, D, E, F. Now we are requesting new memory by doing malloc. Now let's do a new malloc, 16 bytes. Then we are going to the bin for the free ones, free 16 bytes bins. Then we find that there is a free one, and we are going to return this one. Okay, and this is a head, and then the header will go to the next one. Okay. So this is how we reuse a memory or malloc chunk, and we do not need to create a new malloc chunk, right? Yeah.
Is it heap shared almost like different threads or like stack?
So first of all, stack do not share the different threads. They cannot share the same stack. Each of them have a different stack.
Okay.
Yes.
But for heap, like, if you this based on this stack.
Yeah.
Let's say there's 2 stacks and one is clean, and like how different threads handle like.
This is very, very tricky stuff. So first of all, different threads will be able to share. As long as they have the address of that, they will be able to share. But the Tcache trying to let's say, each of them is trying to maintain that local, that structure for each thread. But a memory chunk created by one thread may later technically belong to another thread.
Yeah.
Yes, that's why we all have a key field. Yes, yes, very complicated stuff. They can share. Okay, yeah. So if we do another malloc 32, then we're going to use those E and C. Basically, we use what a head points to, right? So this is easy to understand. Then we can skip this part. Oh, okay, this one is interesting. Okay, now that's what I said before. For the 64 bytes, we don't have any freed one. Okay, then we are requesting a new one. Then we just create a new memory chunk. Okay, a malloc chunk. We don't have a free one to use. We just create a new one. Okay. Okay, finally, we can see some code. Huh? Something wrong with the code part. Just tiny errors. I think I updated, but let me check. just tiny errors. I changed the name, I changed it a little bit. This is why I changed the size T. Okay, but it still works. Let's say we have several numbers here: 32, 4, 20, 0. Okay, 0, 64, 32. Okay. Those are 10 numbers, and we're going to malloc those sizes. Okay. Then we're going to say how big each malloc chunk is. Okay. So let's guess. Of course, this is related to 32-bit and 64-bit. Let's say, let's do 32-bit first. Oh, I forgot to change this one. Oh, this one is correct. It's actually the same code. I just changed the here a little bit, changed the printout a little bit. We are requesting 10 memory or malloc chunks. What will happen is they will be allocated one after another. And they do not have the same size, but they will be allocated one after another. Okay. Even if you go for even bigger ones, will be one another. If it's huge, it could be a different story. Okay. So let's say this program, what this program does is it will first malloc all those 10, then it will print out where it first in print out how many bytes we're allocating. Second, we print out what is this one, PTR, the pointer. This is your buffer, okay? This is your buffer. And we're going to use this one minus this one, I plus one. So the next pointer, the next buffer's address minus the previous buffer's address to tell you how big that is. So for 32-bit, it will look like something like this. You can run this on the server, get the same results. First of all, the 32-bit, so the size T is 4 bytes. The pointer obviously is also 4 bytes. We malloc those from 32, 4, 20, 0, okay, to this. And then we compute the size. So this is the first chunk. This is high and this is low. Okay. This is your buffer's address here. The first malloc returns the address of here. Okay, that's your buffer. But like I said, there are metadata. Metadata is actually before that, 8 bytes in total. And we are computing, and we know that's 8 bytes. We're computing from here to the next buffer, and this is 48 bytes. And in that 48 bytes, we also have 80 bytes, 8 bytes of metadata. So the buffer, we're asking for 32 bytes. We actually get 40 bytes to make the whole thing 48 bytes for alignment. The alignment here is 16 bytes. Okay. So the whole thing is 48 bytes. The second one, we ask for 4 bytes. Okay, only ask for 4 bytes. And the metadata is already 8 bytes. The alignment is 16 bytes. So the whole thing is 16 bytes. The buffer is 8 bytes. The third chunk, I think this is the interesting one in the third chunk. The third chunk, we're asking for 20 bytes. Yeah, the third one, we're looking for 20 bytes. And we got actually 24 bytes for this one. Oh, no, the 64-bit version is interesting. Okay, so here it's easily, you can understand this. This you can understand. This is, yeah, go ahead.
The bottom is written that alignment is actually defined as 2 into 5 of 5. I see 4, right?
Yes, but here it's a typo. It's a typo. Yeah, the here should be 16 actually. Is it at least based on my testing? It's 16. Yeah. I didn't find the code specifically saying it's 16, but my testing is 16. Yeah. For 64-bit is also 16. What interesting is the 64 bits. I think I forgot to explain one thing here, so we need to go back there. This one. For the T-cache version, this previous size field, which is that metadata, the first member in the metadata, this field is not really used. T-cache doesn't use this, okay? Because it doesn't use this, this either 4 bytes or 8 bytes can be used by previous chunk. It's user data can go to here. And that will influence our annotation next. Okay. This is a 64-bit version of this. We're asking for the same bytes. When we ask for, so here, the first one we ask for 32 bytes, and we have 16 bytes of metadata already. With 32 bytes, we have 48 bytes, the whole thing. The second one, we have 16 bytes plus 16 bytes. Even when we're asking for 4 bytes, it actually gives us 16 bytes. So in total, 32 bytes. The third one is interesting. We're asking for 20 bytes. Okay, this one. We're asking for 20 bytes. But the distance from the next one to it is only 32 bytes. So it's this one. Here, this is the third one. This is the address returned to us by malloc. From here to the next one, in total, 32 bytes, like we show here. This thing in total 32 bytes. And the metadata for the next malloc chunk is already 16 bytes, which means the buffer give us is only 16 bytes. But we're asking for 20 bytes. Right? How could that happen? That's because, like what I said, the previous size in T-cache is not used. So that 8 bytes of the next chunk is also used for this buffer. So that's why it has 24 bytes of buffer. For those, actually, it has 40 bytes. Yeah, that's because of that. Yeah, this field is not really used.
40, does it just like all people metadata and put that in?
Which one?
The one?
No. It has to be 16 bytes aligned there. Yeah. Yeah. So the buffer part will be 16 bytes actually. Yeah. That is actually in the document. I will show you. Here. This next slide. So in the malloc comment, it says that if n is 0, malloc will actually return a minimum sized chunk. Yeah. And in this case will be 32 bytes in our system. Yeah, that's why the buffer will actually be 16. Yeah, or 24, depends on how you count that. Okay. So 0 will also give you something, basically. Then let's print this out to really see those numbers. So now we are requesting different sizes of memories, starting from 0 to 16,000, more than 16,000, right? And like I said, they will be allocated one after another, actually. Okay. This is the first time we allocate them. They will be allocated one after another. But later, when we free them, we reuse them, some will not be newly allocated. And right now, they will be newly allocated. So this program will first malloc everything. After that, we will print out the chunk. Okay. We do not only print out the buffer because there's nothing in the buffer. We didn't put anything there. We print out the chunk. What we print out of the chunk is we first print out the previous size field. Like I said, the T-cache doesn't really use that, right? Doesn't really use that. Then we print out the current size field, current chunk size field, and the last 3 bits has some special meanings. That's the 3 bits. It's the PAM bit, but I just print them together here. Then the address of the buffer itself, the malloc, we just print out that. So how do we print out that? Is malloc give us the pointer, okay? That's a pointer. Pointer minus 1. Pointer minus 1. We will get the second field of the metadata. Pointer minus 2. We get the first member's address. Right? Then we just dereference that. Okay. Yeah.
I think where the 3 bits are, is it part of the size?
The 3 bits is in the part of the size. The last 3 bits are part of the size. Yes. Those 3 bits, part of size.
When you read the size report, you have to remove it, and it will come.
Technically, you should, because they are aligned. So those 3 bits will never be used for the size anyway, right? Let's say there are 16 bytes aligned, then the last 4 bits, you're not going to use it, right? Then we use it for something else. Yeah, that's how it is designed. If you go to the CPU design of any architecture, you will see a lot of things like this, because the least significant bits sometimes don't matter, especially when you talk about size or whatever. Yeah, so they were reused as for something else. Yeah. This is totally different from application level design, right? I mean, you use a variable for very simple stuff. Here we are at this level, you are trying to saving every bit there. Yeah. Let's say, where are we? Okay, we're in this program. Yeah, this is the program. Okay, so this is the result on my local laptop actually, but you run on the server, you get a similar things. On the top, we have the 32-bit, bottom we have 64-bit. First of all is this column is a buffer's address. And you can see that they are they're actually one after each other, right? One after another. So the first one is at address 5B0. The second one is 5C0, then 5D0, and get it bigger and bigger. Okay? So they're actually one after another. Okay? So the heap is going from low memory address to high memory address. Okay. Then look at the previous field. The older version, this will be the size of the previous chunk with no T-cache, right? But in T-cache, this is not used. So the previous one is always 0 because we're not using that. Then the size part, forget about that 1 here because that's the last 3 bits, which means the last bit, the P bit is, which one is P bit? Okay. The previous one. Yeah. Yeah, so because the previous chunk is, I'm not sure about the first one, why it has a P1. But for everyone else, their previous chunk is, hold on. The previous chunk is not in use in this case, right? Oh no, it is in use. It is in use. Yeah, yeah. What? Yeah, but that's the least significant 3 bits. Yeah. Yeah, so it's not really the size. This part is the size. So this is basically when those malloc chunks are in use. What does it look like? Next, let's take a look. Okay, when they are freed, what does it look like? And I'm doing this for those small bins. So we're allocating 5 malloc chunks. They're all small, 32 bytes. We first print out, we first malloc them, then we print the in-use chunk, then we free them, then we print out the freed chunks, okay? And the in-use one is similar to what we just saw. We print out previous, size, where the buffer is. That's basically it. And also where the chunk is, but where the chunk is the same as where it's actually the address of this one, that man. Then the freed one, remember, it has a different structure, right? The freed one basically has, you still have the previous size, which we don't use, current size, then we have the next pointer, remember? Then we have the key pointer, right? So 2 pointers there. So we print out the next pointer and the key pointer. Yeah. Yeah. Go ahead. So this is the result. What? Yeah, of course. So first we malloc, then we free them. The malloc part we can skip, and this is the freed one. So what interesting is here, the next field. So this is what we print out after everything is freed, not after we free this one, we print out after the one. Everything's freed, we print this out. The first chunk, it's the first chunk is the first freed one, right? So at the when it was freed, the head directly points to that. Then its next field will be what? 0. Okay. Then the second field, the second chunk was freed after that. It will be inserted to the head. So the head will point to this. Then at that time, this one will point to where? The first chunk, right? So you can see the address here is, the next one is 5B0. So 5B0 is this one. Because here we have 5A8. It's actually the same because we didn't print out the address of that next pointer. Yeah. But they are actually the same structure. Yeah. This address and this address, they belong to the same structure. Yeah. Then when this one is freed, the head points to that, but later, eventually, the head will point to this. And this one's next point to this one, and this one's next point to this one, and this one. Okay. So that is how it works. Yeah. For 64-bit version, actually the same thing. However, the key part for all of them, because the key points to the thread global variable, that structure, that's why the key part, they are the same. Okay. So this is different design from the version of no cache. With no cache, those 2 pointers will be forward pointer and backward pointer for a double link list. Yeah.
Basically, it's built on this thread.
Yes.
And then that wants to allocate some, let's say, the 2016 by something that has been freed earlier. Does it pick it from this linked list and change the key, or does it?
It can pick up here and change the key. Yeah.
Or does it allocate something else for that?
I think we need to do some tests, but I think it can pick it up from here. Yeah. I don't know. I need to do some tests. Yeah, like I said, this is constantly changing.
Theoretically possible.
Yes, of course. Yeah, there's an arms race between security and performance in the memory allocator. Yeah, when when more vulnerabilities discovered, security guys add the security features, making it slower. Then other people try to make it faster, introduce more security vulnerabilities. And the memory allocator is one of those arenas, things change very fast. Yeah. That's actually all I have for today. Yeah. So starting from Tuesday, with those background knowledge, we're going to see how we can exploit this. It will get very complicated. Yeah. Yeah, even this part is a little bit complicated, right? Yeah. And we're not even looking at internally how they are implementing this. There are many ways we can exploit this. That's first of all, there can still be overflow, right? One chunk can overflow other chunk, but that is not directly related to how a memory allocator is designed, because that's basically a buffer overflow there. Then let's say you can mistakenly free the same memory chunk twice. You can create a fake memory chunk and ask memory allocator to free it. There are many tricks we can play. Yeah. So cool. Any questions? Okay, we're good. Okay. This week homework is about the format string, right? So I guess you guys will be good, I guess. Okay. But if you need any discussion, just ping me on Slack. We can have an office hour. Next week homework will be raw. So I guess some of you will need some help. Yeah. Yeah. We're almost there. We have only 4 more sessions. And I think we will maybe spend most of time on Heap, yeah, for the rest of the sessions. Yeah. In my previous classes, I also covered the cache, but I guess we may not have time for that. But I can send you guys videos later. You can watch that. Yeah. Cool. Yes, I guess that's it for today. See you guys next week.
Yeah.
Thank you.